Thank you everyone for coming. It's an honor to introduce Abhinav Gupta. Thank you very much for coming. We know that you have a very busy life. CMU, Facebook, and a 10-month-old baby. So that's fascinating. And again, thank you very much for coming. We know that it's difficult to make it. So Abhinav is an associate professor at Carnegie Mellon, the Robotics Institute. And at the same time, he also is a research manager at Facebook AI Research, which is exciting because maybe we'll get to learn a little bit about both Abhinav's vision, but also Facebook's vision on research in robotics. And Abhinav has sort of that vantage point where he is both a computer vision person and a robotics person. In fact, he has received like awards, paper awards from both communities. And we all say that these two communities should sort of cooperate more and work more together. So Abhinav, I guess that's happening inside his brain all the time. And it would be great to get that perspective and learn from it. Abhinav is interested in that sort of vision of self-supervision and sort of lifelong and to some degree unstructured learning, and how do we get that to work. And it's something that he has been advocating for quite a long time already, and it'd be great to learn more about it. Thank you very much for coming.
Thanks, Alberto, for this generous introduction. All right, so I guess as in many presentations, the first slide is the real deal, which is like I haven't done any of the work. I mean, this is work of mostly all these students and people at Facebook and CMU. And in fact, I did recount there are four people already in this crowd of these people, like Tao, Pratyusha, Rohan. I mean, so they have been interns at Facebook or students at CMU and now moved on to MIT. So that's great. So there are a lot of familiar faces around. All right, with that, I guess all of us, since we see such a big crowd, we all know what's happening, right? I mean, there's so much excitement in computer vision, artificial intelligence, robotics, and all this field. And a lot of this excitement has come from these advances in large capacity networks, deep networks, some people call them convolutional networks. There's so many names. You can neural networks and so on. But if you think how we learn these networks, or what kind of learning that happens behind them, is still kind of very, very narrow in scope. Now let's take up two success or hot areas. I'm going to call them hot areas. Are they successful or not? This is questionable. But the first hot area is computer vision. So how does a computer vision system work? The first thing you do is download millions of images from the internet. Then you start labeling them. There's a dog here, there's a cat here, there's a mushroom here, and so on. You would label 200 different types of dogs, 200 different types of mushrooms, and so on. And then what you do is you learn this non-local function, which is the neural network, in a supervised fashion. That is, you are asking this network to predict these classification values that you have marked, essentially. So this is supervised, and it's passive. Why is it passive? Because the network or the agent has no control over the data. We randomly downloaded images and gave it to it. And so now there's no control over the data. Now the second hot area, which I am sure all of you have also heard, which is more closer to you guys, is this area where we basically fix a task, Atari game, or a Rubik cube, let's say. We basically, once we fix the task, we are going to define the rewards by hand designing some function in the environment. So this is mostly in simulation. And then what we do is we spend hours and hours of cluster time, thousands of GPUs or thousands of whatever CPUs, and we do something called reinforcement learning. And what we learn is to solve that task itself. Sometimes you can show that it also transfers to the exact same object in the real world, but you are learning that one task, essentially. Now, so this is what is hot right now and why we are also excited. But compare this to what happens in the case of humans, or how the most intelligent machine that exists. I mean, it's very, very different. The story of learning is quite different. First, in the case of humans, we are not labeling mushrooms and dogs in case of like visual representation learning. Most of the learning happens in unsupervised or self-supervised in nature. Similarly, when we are trying to learn representation of policies for actions, again, there are no environment rewards. The world does not give you rewards in the way these simulators give you, essentially. Second, most of the learning in case of humans is happening in physical real world, not in the simulators or not in this mainframe which is downloading lots of images, essentially. It's very different from what we are doing right now. Third, in case of humans, we are not doing passive exploration. We are not just getting passive. We are not passive learners. We are active learners. And so you can argue that reinforcement learning is active exploration but our kind of active exploration is hugely different. Because in all these reinforcement learning, exploration is always in a context of a task. You first define a task, and then you go explore in that environment to solve that task. In our case, there is no task really defined. We are just defining our own task and exploring our own data, creating our own data points. And we then decide what's the next data point we want to get. I know how to push this bottle. Maybe next time I want to see what happens if I throw the bottle. That's what babies essentially do when they are trying to learn. Then in the case of humans, you are learning for diverse tasks. You just don't solve one task at a time. This is what we are really good at in both the other, both in computer vision and reinforcement learning, solving one task, either classification and so on. In case of humans, we are learning from diverse set of data, very diverse data, and very diverse tasks. Learning is multimodal, as you can, we are not learning different models for audio, vision, and so on. We are learning one common model. And our learning is very continuous and lifelong. We basically continue to learn every day, essentially, and we reuse. There's a lot of reusability of knowledge that we do. But I would argue, forget all these reasons. There's one big reason why these approaches are just wrong. Both these approaches are just not scalable. Let's look at the visual approach, right? In vision, the way we have been solving our problems is by labeling lots and lots of data. And so ImageNet, which is one of the biggest data sets in computer vision, has labeled 1 million bounding boxes in 5 years. But if you think of how much data that exists in the world, Facebook has, for example, more than 600 million images uploaded daily, and that's a pretty old number, essentially. So let's look at the other side, which is the world of actions. In most of these cases, you basically use tens of millions of iterations, and you basically solve one task at a time. Now compare this to what humans, like a 3-year-old baby can solve thousands of tasks, essentially. So clearly, this also is not scalable. You cannot be doing tens of millions of iterations for thousands of tasks. This is just not going to scale. So to tackle these problems, my research has been focusing on building self-supervised, curious robots. And the key principle is, I want to learn about the world by physically experimenting in the real world. For me, physical world is very, very crucial. And that's what is critical to learn about our world. I also want to say, in a much more simpler language, I want to build robots that will learn like babies. And I said loosely because, of course, we don't know how babies learn. I mean, there is a big question mark there. But just very loosely inspired from babies. We want to build up our learning systems which are very similar. Now, if you think of babies, there are lots of different stages of learning in babies. So the first stage is this passive stage. This is the time when baby is born. He or she is lying down. They're not really starting to interact with the physical world yet. But they are seeing a lot of visual data around them. They see their parents interacting with objects. They see parents interacting with themselves, with the baby itself, and so on. So at this stage, basically, you're going to use all this visual data, or lots and lots of visual data. Now, the baby does not have any control. So that's why the first stage is kind of passive in that sense. We are going to use it to learn some kind of visual representations. What are the right features? What is the right forward model of the world, and so on. The second stage is when baby starts interacting with the world. Initially, the baby's interactions are quite random in nature because it's first trying to learn how does the world behave with different actions, essentially, right? It needs to seed up its learning. And this is the seeding up stage where you start with random exploration and you basically start to learn about some basic primitive actions, essentially. Then the babies start to get smarter. I mean, they are now going to explore actively. They are going to create hypotheses in their mind. They are going to say, okay, if I can roll this, it behaves like this. So next, let me try to throw it, and so on. You create your own data points. You play with toys. You see, okay, how the world behaves, essentially. The fourth stage is when babies start to imitate basically the other humans around, which is mostly their parents. So if you do some action, they will try to imitate that action, and so on. And the fifth stage, which I call the social stage, is when babies start interacting with other babies. They learn in the presence of other babies, like in a daycare, or other babies in a music class or something like that. And at this stage, babies also start getting manipulative. And here I call, they are basically so manipulative that they can guide their parents to give them the right supervision if the parents are not giving them the right supervision. So this is the 5th stage, essentially. Now in this talk, I don't have time to go through all the stages, but I do want to talk about the first 3 stages and our work in this direction. So I'm going to first start with talking about this idea of learning visual representation. What is the right visual representation and how can we learn it? Instead of trying to learn from lots and lots of label data, we are going to try to learn this representation directly from data itself, no labels of dogs and cats and so on. But of course, as I argued, this is just the first step in learning. The much interesting step happens when babies start interacting with the world. Our learning looks something like this. We push objects, we poke objects, we throw objects around, put objects in our mouth, and all these things are going to help us learn models of the world, essentially. So in the next stage, second part of the talk, I'm going to talk about how we can do physical learning with robots, and what I'm going to focus on is how critical is data in robotics, essentially. And we are going to focus on how we can learn in the real-world environments, real-world tasks, and basically hardware as well, like what would be the good hardware and so on. And then finally, I'm going to talk about when babies start to actively explore without the context of task. They are exploring with their idea of curiosity, or like they want to figure out how the world behaves. So they'll basically generate their data points to understand the world as themselves. So these are the 3 stages of the talk, 3 parts of the talk I'm going to talk about. I'm going to keep the first one shorter because I know this is a robotics seminar. But as Alberto said, that I am a computer vision researcher as well. So the characterization of my research will not be complete unless I talk something computer vision as well in this talk. And so I'll try to keep it as short as possible, essentially. Now I do want to mention that we have been doing a lot of work. So I'm going to go through all this, but multimodality, we have been doing a lot of work. For example, we have been building this something like a tilt bot, which basically takes objects and basically tries to learn correlations between audio and vision and action. So it's like a data set which is like what kind of audio is created if you apply what kind of action. And we are basically learning predictive model in this joint space as well. And so this is something which we have been looking at. And similarly, we have been also looking at this lifelong learning. Specifically, we are looking at how we can scale up common sense learning, semantic common sense learning with lifelong learning, essentially. Just briefly, we have been building basically this system NEAL. NEAL stands for Never Ending Image Learner, which runs 24 hours a day, 7 days a week. It downloads images from the internet, use these images to learn models of the objects, for example, cars and so on, labels objects in these unlabeled data, and then learns common sense knowledge. For example, cars run on road, cars are found in parking lots and so on. And it basically builds upon its knowledge. So based on whatever it has learned, it goes to the next step and learns more and more common sense knowledge, essentially. And so this is something which we have been also working at, but again, I'm not going to focus on in this talk. Okay, so back to the talk and not derail myself. So let's start with the first one. And the first stage, what we want to do is we want to, Abhinav, feel free to ask questions at any given point of time if you want to. So the first stage, we want to basically perform self-supervised learning, basically learn visual representation, what are the right features and so on, but we want to do it without labels, essentially. To understand how we can do that, let's take a step back and see how does supervised learning work. So as I said, our data sets look something like this, where you have an image and you say what is in that image. So for example, in this image, it's a beagle. And what you try to do is, you try to learn a neural network, which is a nonlinear function, to make these predictions. And our hope is that by learning this function, we somehow magically factorize things like material, geometry, parts, and so on. Because if we can factorize these different things, then our representation could just transfer to other tasks, for example, pose estimation, and so on. And so the question that we want to ask here is that there is something specific about this task of classification that we can actually learn these representations that transfer better than anything else, or is it something else? Because if we can get rid of these semantic labels like beagle, and we can automatically generate ground truth labels or for some task, then we can get rid of this problem of labeling data, and we can just use all the images on the web and scale up our learning to billions of images rather than work with 1 million images which have been labeled by the ImageNet. So in our research, what we have been looking at is a concept of pretext task. So these are the tasks for which ground truth is going to be free. and yet they will, to solve these tasks, you will need semantics. And so by solving this task, you will always get ground truth free, but you are learning semantics while you're trying to learn to solve this task. And so let me give you an example in natural language processing of what is very common. So hopefully some of you have heard this representation called word2vec. And what they do is, let us say I want to learn a representation for the word appliance. So what I'll do is I'll try to learn a representation of word appliance by predicting the word that will appear in the neighborhood of this word. And so I need to learn a representation such that I can predict store-bought, toasters, and so on. And so now in this case, you can see the ground truth is free, right? I just need to see what other words occur in the context, and I can download image like paragraphs of text, and I know what words should appear. So these are the words that should appear. And so now I can train this representation with this task essentially of predicting the neighborhood words. So can we do something like that in images? Because images are even richer than text. Text is linear. Images are 2D, and they have spatial structure. So can we do something like that in the case of images? So let's look at one task. For example, let me show you these two patches and ask you how they are relatively spatially located to respect to each other. What is the relative spatial location of these two patches? Let me make it a little simpler for you guys. I'll keep the first patch in the middle, and the second patch appears in one of these 8 locations. Hopefully all of you can solve this task of where the second patch appears, and hopefully all of you are thinking of this answer. And the way you solve this task is by recognizing that these are parts of a bus. So the top of the bus is coming from here, this patch is coming from here, the other patch is coming from the wheel, and this is the general location of the 2 patches with respect to each other. Now you can see the task I gave you was predicting the relative spatial layout. This is free task, the ground truth is free. In any image, I can pick any 2 patches, and I know how they're configured with respect to each other in the relative spatial layout. But to solve this task, you have to use semantics. So these are the kind of pretext tasks that we can use to train in a self-supervised manner. So the approach is going to be simple. Given an image, you find a random patch, then sample another second patch from the neighborhood. Now you know the answer to your problem, which is what are the relative spatial location of these 2 patches. Now you try to learn a network representation that can predict that. And hopefully to predict that, network is solving semantics, and you can now use this representation that has been learned for a task. And so we basically tested it on object detection. So if you're not using any pre-training learning, you get 39.7 mean average precision, for example. If you're using ImageNet as pre-training, like labeling dogs and cats, you get 70.9. But if you use our task, you get 62.6. So it's not as good as supervised learning, but at least it's making some impact. It's better than just using completely from scratch, essentially. So what it says is that we are able to learn some kind of representation, but not as good as supervised representation. And so just trying to understand what this approach is good at. It's good at knowing 2 cats are same class. For example, because the relationship between the eyes and the legs remains similar. But when the cat deforms, the pose is changed, then it gets confused because the relationship between the eyes and the legs is now changed suddenly. And so it doesn't put this cat into the same category as these other cats. So this approach of pretext task is good at instance invariance, but it's really bad at viewpoint and deformation invariance. So for getting something like viewpoint or deformation invariance, we need something which says that this is a bottle, this is a bottle, this is a bottle, this is a bottle, and so on. So how can we learn something like this, viewpoint or deformation invariance? Well, I just created a data set myself. If someone was recording, and there is a person recording this video, they could have used this video, figured out that this is the same object in different frames, and use it to learn the viewpoint invariance. And that's what we do. So we track up objects in videos. We basically use the first patch of the track and the last patch of the track, and we try to learn a representation that will keep this first patch and the last patch close to each other, because they will be in different viewpoints essentially. And so with that, you can learn a representation that is going to be viewpoint and deformation invariance. So this approach is going to be really good at it. In terms of numbers, where will it lie? You can basically get 62.2 with the tracking viewpoint deformation invariance. Now you want to still get closer towards supervised, so we can try to combine the two because both of them are learning different kind of invariances. You can get 65. And now we still are coming close to this supervised performance, but it's still far. So the question is, how do we bridge this gap? So one way is we can come up with new tasks. Like I came up with 2 pretext tasks, you can come up with more and more pretext tasks. And there has been a lot of work that has been happening in computer vision on this area of coming up with new pretext tasks and learning a new representation. Some of it here at MIT as well, for example, like sound and depth. Sound one has been at MIT as well. Instead, we go back to the first principles. Remember, the principle, the reason we started with self-supervised learning was it will help us overcome the labeling bottleneck. So most of the self-supervised approaches will still train on ImageNet, which is 1 million images. Remember now, we don't need labeled data. So we can really scale this up. We do not have to be restricted by 1 million labeled images. So that's the first thing we try to bridge the gap. What if we try to just do this, scale this current approach to 100 million images? And it turns out that when we do something like this, with 100 million images itself, it's all like 14 million images itself, it starts to, the gap starts to close, and it is within the error of like repeating the performance, within 1% error essentially. And so that tells you that the scalability argument that self-supervised learning approaches have been making is pretty good, and you can really get good performance by scaling these approaches up to 100x data, 1000x data, and so on. So just to let you know where the performance lies, so self-supervised learning is really competitive or better than supervised learning in tasks like object detection, 3D scene understanding, visual navigation, and so on. But when it comes to classification, self-supervised learning is still, there's a long way to go. So you still learning using supervised learning is much better than using self-supervised learning, essentially. Okay, so that is the first part of the talk, which was vision, but that is something I did want to talk about before I moved into the robotics part, essentially. Okay, any questions or anything? All right, so let me move into the robotics, which is the main feature of this talk. So as I said, one of the things that I personally want to focus on is learning in real physical world. I believe that is the critical thing that we require to learn for intelligence, essentially. When 2015, when I was a vision researcher and I started moving to robotics, I found out that, okay, I wanted to do this large-scale learning in robotics, but most of the data sets in the robot learning community were something like this, and the maximum size of the data sets would be 1,000 examples and so on. So there were these big questions in front of me. For example, is big data even useful in robotics? What if this is not even useful in the case of robotics? And then the second one, which I had also, is can we actually collect large-scale data set in unstructured environments with our robots, current robots themselves? And so with these two questions, I started looking into how can we scale up robotics and what can we do with large-scale learning in robotics. So as a first step, we tried something very, very simple. We built this robot. So this is a Baxter robot, but we basically, the setup is there's a robot and a table in front of it, and we basically choose a random location, and we try to go and grasp at this random location. So you can see this is a randomly chosen location, it grasps nothing. Here's another random location, it's going to grasp nothing in this case. The way we are going to measure the success and failure of a grasp is by the force sensor in the wrist. And so when the grasping is going to be successful, the face turns happy, as you see in this scenario. So you can see whenever it's going to be successful, the face is going to turn happy, and you know that you have been successful in lifting an object in this scenario, essentially. Now you do this not one time, not 2 times, but we did this 50,000 times. So we basically ended up collecting a data set of 50,000 different grasps, and that amounted to learning 16 hours per day. We ran our robot 16 hours per day, and for a total of 700 hours. So this was one of the first data set which was basically going into this range of 50,000, like 10 times bigger than any other data set in robot learning at that point of time. And once we had such large data set, we can now think of learning these end-to-end networks and see how good the performance would be. So for example, in this case, we learned a simple network which, given an image patch, will basically try to predict what grasping. So you take an image patch, you basically send it through the network which is inspired by ImageNet network, and then at the end you basically classify whether this grasp is going to be successful or not, whether this grasp is going to be successful or not, and so on. So you have 18 different discretizations, and you predict which grasp is going to be successful. And you learn this with all the 50,000 examples that you have collected, and then you test it on the objects you have never seen before. I think that is one of the critical things. You have to test it on novel objects. We did test it on training objects as well to just given performance. They test seen objects. These are previously seen, but these are unseen objects. And you can basically see that the performance, the thing starts to work reasonably okay. So for example, with increasing amount of data, you can get better and better performance. You can do things like clutter cleaning and so on. You do start to see some plateauing at 20,000, 40,000. But that is just because we do not have enough diversity in our training and test objects. I mean, so we need probably more diversity in our training and test objects essentially. But this was our first case where we saw both the questions kind of seem to be answered for me. Like A, you can collect large scale data in robotics, at least up to the scale of 50,000. Maybe you can do more. And then B, large scale data seems to be really helpful even in the case of robotics. So data seems to be a critical commodity which has not been explored as much in the case of robotics. Following our work, for example, Google Brain did used 14 arms to collect 800,000, and then they showed even at that much scale, the data seems to be useful and so on. So we were inspired by this. We said, okay, if we can do self-supervised learning in case of grasping, maybe we can do it with drones as well. So how would the self-supervised learning look in case of drones? Well, we built a drone whose only goal is to go and collide into objects. Okay, the only goal of this drone is to go and collide into objects. So it basically, the drone chooses a random direction and goes and collides into that direction with the object essentially. So we made this drone collide 11,000 times and in 20 different environments. And again, what is this trying to get? This is trying to get data of what a drone should not do. This is all the negative data. These are all the collisions you should be avoiding essentially. So what we were interested in is, if at this scale of data, will the drone start to do something interesting essentially? Like, can we learn a reasonable obstacle avoidance algorithm for a drone? And the approach is again going to be very, very simple. Again, what I'm trying to show is lots of data, simple approach can actually make things work reasonably okay. So for example, in this case, when the drone is far from the obstacle, we say it's a positive. In the middle, we are going to call it gray zone. We have no idea. And when it's just going to collide, we call it negative data. This is exactly what the drone should not do. So we basically label the data automatically in this manner, every trajectory. And then we again learn a simple network inspired by the ImageNet architecture, which given an image, tries to predict whether it's safe to go forward or not. And we have both examples of positive and negative. At test time, if it says it's not safe to go forward, we have to decide whether to turn left and right. So basically, we also look at the left image, left crop, and the right crop, and try to predict whether it's safe to go in the left crop and the right crop with the same network architecture. And based on where it's the safest, we just basically turn in that direction. And with this simple algorithm, we basically can learn a really interesting policy for obstacle avoidance. So you can see in this case the Wien Hall. Some of you might have been to CMU. So this was the scene that was never seen in the training time. And now it goes towards a library in the Wien Hall. It recognizes that there is an obstacle here. It will turn left and continue in that direction, essentially. Here is a case with the Smith hallway. We put some chairs to make it hard for the drone to avoid. And you can see it basically avoids both the chairs. It's basically going to now go towards a door. It recognizes it as it tries to take a turn. There's not enough circle, so basically it collides a couple of times, and then basically it's fine again, essentially. And so again, what we are trying to show is that with real-world example, you can reasonably learn obstacle avoidance easily. During training, we had students. When we were collecting this crash data, sometimes it did crash into students once in a while, so it knows how to avoid students or all the negative data as well. So it does avoid the students when they are walking or something like that. So yeah, I think it can avoid dynamic obstacles like at least humans. Okay, so this was a second example for us where we came to know, okay, lots of data, simple, seems to work reasonably well. We don't need to model everything in the world, essentially. But this answer, the way I started, right? I started my presentation saying, is it scalable? So now someone can ask, is this scalable? Like creating drone for 10,000 times or having robot grasp 50,000 times. Is this learning going to be scalable or not? So as a next step, we wanted to see what if we try to learn for different tasks together. We try to do some kind of multitask learning. So we take 3 different tasks like grasping, poking is basically pushing into an object, and pushing. And so this is the pushing task where you hit the object. I don't know why the video is not running. But for these 3 tasks, you learn a common model, and you want to, so this is the pushing task. You're basically trying to push from one x, y location to another x, y location. And you basically collect large-scale data for this, and then you learn a common network that is going to solve all these 3 tasks. And so what we are trying to see is, do I need 3x data to get similar performance, or can I somehow save on data when the 3 tasks are learned together, essentially? And I think this is one of the most surprising findings from machine learning perspective. Generally what happens is when you train on VOC data or some data set 1, and you test on that data set 1, you get the best performance. If you take the data set 2 and you replace data set 1 images by data set 2, you will not get as good performance. So every data set comes with its currency, and you get best performance when you're testing on the same data as the training data essentially. But in this case, for the first time we found out that when it comes to robotic tasks, like especially like grasping and pushing, it is better, like even if you keep the total amount of data constant, it is better to have diverse tasks rather than same task, even for that task itself. So what does it mean? So you will do much better on grasping if you have 2,500 examples of grasp, 2,500 examples of push, rather than 5,000 examples of grasp itself. So you can basically improve grasping performance by seeing more push data. And that seems to be very surprising from most of the machine learning, because in computer vision, natural language processing, any machine learning task, this doesn't seem to hold true in most of the cases. And we basically studied this for the different data points, and it seems to hold true. When the data point is too less, at that point it doesn't hold true. Like if you have less than 400 examples, then it's better to just get more grasp examples. But at some point of time, it's just better to just mix your data essentially. Now there are multiple reasons that could be, for example, regularization. You might be getting regularization from these different tasks, especially because you are in this regime of less data, 10,000 data, and so on. If you are maybe in the regime of 1 million data, probably then at that point it does not matter and so on. But at least it seemed interesting, and it seems to suggest that multitask learning can be critical and maybe can help us solve some of these problems like of scalability and so on. And so that bit, yes?
So the way you're solving the graphing, it really does look like a computer vision problem. Like you're just classifying whether some bounding box is a good grasp. So I guess if you mentioned a few reasons. So if you just took 10,000 images from ImageNet and then VOC and redid this, just basically made those computer vision tasks look the same as these in terms of size of data and stuff to do the results. Sort of, is it just about the data or is it about these tasks?
So that's a good question. I mean, I think I'm going to now generalize to tasks a little bit later. I agree. So one of the criticism, at least in the first part of the talk, in the second part of the talk, is going to be data. In the third part of the talk, hopefully that I'm going to start to get rid of by going for other tasks like example opening bottles and so on as well. But yeah, you're right. In fact, I would say even more pointed question. Like some of these large-scale data collection is only possible in these kind of tasks themselves, like pushing, grasping, and so on. It's very, very hard to collect data of opening bottles by randomness. That's basically what you're asking. And I think you're right. And so I think that is a critical problem in my formulation, but hopefully the third part of the talk is that's where I'm going to talk about some of these issues. Yes?
So the premise of the first, like the drone example and the grasping example is a self-supervised, right? But in both cases, you have a supervision signal. In the grasping task, your supervision signal is whether you successfully got in your grasp, and the second one, your supervision signal is a classifier that says, yes, you're going to hit, you're great, or something.
Right.
So can you help reconcile the idea of self-supervision versus this lightning situation?
Right. So the way I define self-supervised learning is when the data itself can give you signal. There's no human in the loop to create the signal. Now, if you are looking at data as not just images, but images plus sensor readings, then the data itself is creating all that supervision essentially. So a lot of, just to complete my thought, a lot of people will look at the videos and train their representation of vision from audio. So instead of audio, just replaced by the force sensor, and now it's basically the force sensor reading. So the way self-supervised learning is defined, and then again, I think you can ask these many questions like, is reinforcement learning self-supervised learning or this self-supervised learning? There is a very fuzziness in these definitions. I'm going to not argue on that. And so for me, and so now when it's fuzziness, it's my prerogative to define, at least for my talk, this is what self-supervised learning is. And so for me, self-supervised learning is you are getting data stream. You are not having any human in the loop. Now you can take some part of the data to predict the rest of the data. And that's what I'm doing. I'm using the visual data to predict the sensor data. And that's what it is in my definition self-supervised learning.
Following up on that, but a human decided where those boundaries were, right? A human decided that if this is your force signal, then this classifies as success or a failure. It's a little bit more than just the signal, right? It's your interpretation of the signal that's driving the learning.
So yeah, I think that will not matter. You can directly predict the signals as well. So for example, in the poking, you directly predict the curve of the signal, essentially. So I don't think that is a blocking issue in this case. So you could have predicted directly whatever there was in the sensor. So I don't think that would not work.
So a question about this accelerated learning by combining the two example tasks. It seems like one of the commonalities here is that there's like an underlying rigid body dynamics. Is it possible that learning that model directly could accelerate the learning of each of these tasks? Because both the grasping task and the pushing task rely on a model of like how.
So what was your question? So the question is what?
Could including a model of those dynamics in.
Oh, right.
Just
yes, I mean, so you could definitely define a model, and that might make it a little faster. You couldn't help, but I mean, at least in this talk, I'm going to avoid using hand-defined models as much as possible because I feel, and this is again a matter of debate. I'm not saying there's a right answer somewhere, but whenever you design hand-defined models, you make choices which we don't know it's going to hold on for other tasks as well or not. But so in this talk, I'm going to let the data decide. Only very basic definitions you can provide, like world is 3D and so on. That is okay to provide, but not detailed hand-defined models. Okay, so being a vision person, in my mind, I was like, okay, I can learn representation for these actions. Is this representation good for other vision tasks? So if I use a network that is learned for grasping, pushing, and poking, and I use this network for, let's say, image classification or image retrieval, is it going to work? And we found out that you can use something, physical tasks can help in visual learning, but there's still a long, long way to go. And multiple tasks, as I said, is useful. You should do multitask learning and so on. But as I said, even in robotics questions, like, I mean, as you can see, there's a plateau coming in, for example, grasping performance, or even in vision, like if you're trying to learn visual representation, we still see there is still a long way to go. And so that made me think around 1.5 years ago, like, what is the problem? What are we missing that if I keep up scaling the data, it still starts plateauing? Whereas nothing starts plateauing in vision for millions of data points as well. And I think the right answer here is diversity. And diversity is one word which I think bottlenecks robotics dramatically. And it manifests itself in 3 different ways. And I'm going to talk about all the 3 different ways which will help, I think, improve robotics specifically. So the first is diversity of environments. This is what, when it comes to personal robotics and unstructured environments, this is what most of the data sets look like. And so this is the lab setting. And my favorite joke is, by just looking at the image, I can tell you which lab this image comes from. If the cloth is green, it's Berkeley. If the cloth is white, it's CMU. Because we just do not bother to even change the cloth on the table, essentially. You can go and look as many papers from the Berkeley lab, or you can look as many papers from our lab. Whenever it comes to lab setting, the data is so biased that without looking at anything, you can just even tell this thing. And that tells you how bad, when we say robot learning we are doing, how bad data sets we are creating. We are creating hugely biased data sets when we are doing robotics inside the lab. And then there is this simulation. A lot of people like to do robotics in simulation. This is what simulators look like. They are horrible in not only visual part, which is fine, I'm okay with that, but even in contact dynamics, they're really, really bad. And so I feel as long as we are learning from these kind of, and in most of the cases, the objects are pretty limited when it comes to simulation as well. I think we really need to have diverse data. Diversity is critical for generalization. Remember, we are starting this whole talk with generalization. We are saying that training and testing on same object is just fundamentally wrong. We have to show that it can generalize. Like you learn on grasping on 10 objects, but you have to show on other 10 that it works essentially. And so what I have been super excited about is we can only get diverse data if we start collecting data inside the real homes of people. We really need to take robots into homes of people and collect data right there itself, because that's where the diverse data lives. However, this is a room full of robotics people, and they will ask, the first question that I always get asked when I say this is, are we even ready to move into homes? This is like, what are you talking about? We don't have a robot that can grasp objects properly, and you want to move robots into homes. And there are 2 problems. A, robots are too expensive. How many people want to buy $40,000 robots that does nothing, essentially, right? And then they're too brittle. They might work for one time, but then they're not going to work next time. And so we have to solve these 2 problems, right? So for the first problem, the expensive problems, we have been trying to assemble a low-cost version of the robot. This is a robot that costs only $3,000 something, and it has an arm, it has a mobile base, so it can move around. And so at least what this does is, I mean, it provides some kind of scalability in taking into this robot into multiple homes and collecting large-scale data, essentially. So this is the expensive part, but then there's a too brittle part. That current robots are just too brittle. Here I feel we have a chicken and egg problem. My argument is that we cannot make good robots until we have enough data in from homes. The second argument is, I cannot put robot into homes until we have good enough robots. So this is a problem that we just cannot solve because there is like a circular argument that we are getting into here. And so our solution was to just start renting homes in Pittsburgh. So it turns out that in Pittsburgh, Airbnb homes are very cheap, $75 a night. You just rent a home, take your robot to that home, start getting the objects from the shelves, put them down, and start collecting the data in that home, essentially. We take some objects of our own, some objects from that Airbnb, and you can now start collecting data inside these 15 different homes that we collected for this experiment, just to see is the whole idea that diverse data is useful, critical or not. And so we collected data from 15 different homes. Now, of course, I started by saying that I'm going to cut down the cost of robot by doing this low-cost robot. What does it bring? It brings bag actuation. So whatever your millimeter accuracy you can get from your KUKAs and stuff, now there's no more millimeter accuracy. You're talking centimeter accuracy. And so the question is, can we do anything useful with that low-cost robot? So to target that, my philosophy is build thousands of robots, cheap robots. Scalability is provided by the cheapness, and then with this scalable robots, you can do machine learning on top. That is what we are good at. Let's just do machine learning on top and figure out the errors right there. So this is what we are going to do. This is the original network that predicts whether the grasp is successful or not. This is the noise modeling network. This is going to predict if you tell it to go to X, Y, where will the grasping gripper end up at. And so now you basically have this probability function, this another probability function. You can marginalize and you can say, okay, if I said go to this location, this is the probability that will end up here and success and so on. And so you train it in an end-to-end manner, and you train your grasp network, and then the results that we got are hugely surprising. And this is my favorite part of this paper. I mean, there's this part of Airbnb homes, which looks cute, but the results are the best thing. So generally, again, we started with this hypothesis, or generally in computer vision, that's what happens, right? You train on data set 1, it works best on data set 1. So if you train on the low-cost home data, it works better even in the lab setting. So you train on lab data, test in lab data setting. You train on home data and test in lab setting. The training on home data seems to work better. And that, I think, is very surprising, and it's a big difference itself. So now it clearly shows that we are not overfitting to the lab setting anymore, essentially. And so it seems that this seems to be learning something more about grasping. It generalizes well. But interestingly, it also seems to transfer across the robots as well. So you can train on this low-cost robot and transfer on Baxter robot, and it seems to be working reasonably well. I mean, this is position control, so that's why we can transfer. Of course, if for torque control, it's not easy to transfer. But there are still the properties of Baxter that are different, like the way it behaves in this noise and everything. But it still seems to work reasonably well, essentially. And so that kind of tells us that using diverse data is critical and can help us learn really good representations. The second thing is diversity of task. You really want to learn not just one task, but multiple tasks at the same time. And the big problem in robotics is most of the papers are first fix a task, then solve the problem. I think that's where we went wrong initially itself. You should not have fixed the task. We should solve for multiple tasks at the same time. This is what humans are good at. Not one task, lots of tasks. Maybe not even, most of our learning is not even task dependent anyhow. And so this is work from Pratyusha, who's here somewhere. And so what we have been looking into is how we have been developing this MIME data set, which is large-scale demonstration data set for 20 different tasks, like pouring, opening bottles, typing on keyboards, and so on. And we want to build representations that can work on all these tasks together at the same time. The third thing is diversity of hardware. I'm going to run over time significantly. I'm not even halfway there. Okay, anyways. So this is a diversity that does exist in robotics. Every lab has a different hardware to begin with, right? But everyone thinks this is a curse in robotics. That, oh, I cannot use that code because it's on a different robot. And so this is a diversity that exists, yet is taken as a curse. And I think that is something which is wrong. The reason being, we should learn policies that should take also into account your hardware capabilities, essentially. So this is a vector that represents somehow the hardware capabilities, and your policy should be such that the same policy should work across different hardwares itself. So there should be some generalization across hardwares. And so this is the work of Tao Chen, who's also here in this crowd. And so basically, we try to learn a policy from these different robot designs, and then we tested on a completely different design that was not seen before, and we can show that it does generalize from one robot to another, essentially. Okay, so this is the second part. The third part is basically exploration. Till now, I have been basically starting, I say, oh, let's try to grasp randomly, and then learn a policy from there. But we know that random is just hard, and someone argued that in random, it will only work on grasping because 8% of the times grasping in random is successful. Here, if you are trying to do open bottles, it's just not going to work, essentially. So we need some better way of exploration. Random is just not going to work. In RL, exploration has been studied a lot, but it's always in context of a reward, essentially. And so exploration is something which has been studied a lot in both RL and robotics. But the big problem is, and there has been recent work in curiosity, which basically tries to predict future. And when you cannot predict future, it tries to explore in that part of the space more and more, because that's where you don't know much about the world. But all this work, and this is, I think, Pulkit, yeah, this is Pulkit's work as well. But in all these things, it still takes tens of millions of iterations to learn anything meaningful. It's highly sample inefficient, and that also is on a Mario. Consider now if you have to make this work in a real world, it's probably never going to work. So that is why in most of these papers, you see lots and lots of simulation example, but never a real robot. Even though you can say that, okay, you want to really test it on real robots. And then there's a second problem, that most of these exploration and things tend to get stuck in stochastic environment. So if you have a maze, you use curiosity to explore, it's fine. But now if you put a TV inside a maze, because you cannot predict the future in this scenario, you just tend to get stuck here. You try to predict future, you cannot predict, you say, okay, let me just stay here and try to keep predicting. And so this is like getting stuck, but in case of humans, you should at some point of time realize that it's never going to be predicted properly, so let's just move on and learn something else, essentially. And so how can we basically try to improve this thing? And so I'm going to jump through. I'm now going to be, since I have only 10 minutes, right, Alberto? 2:50. I should stop at 3, right? Yeah. Yeah, okay, that's fine. Yeah. All right, so I'm going to, okay. So the reason these current approaches are not sample efficient is because in most of the cases, you are basically trying to predict future, and because you have to, and the reward function is the difference between the predicted future and the real future. Now, because you do not know the environment function, it's impossible, it's not easy to differentiate, and that is why you use the black box, environment is a black box function, and so that's why you use the reinforce operator to train this exploration network, essentially. So instead of using a prediction model, just single prediction model and comparing the future, what we do is we learn multiple prediction models of the future, and we just decide whether these prediction models agree with each other or not. And if they don't agree, that means we do not understand this part of the world properly, and so we should try to learn we should try to explore more in this space, essentially. And so with this, so because it doesn't depend on the environment, it's fully differentiable, and we can basically learn something useful. I just want to show the results on the robot. So we tried this on a real robot, and you can see with just 1,200 examples, with just 1,200 examples, the robot already starts to do something interesting. So remember, tens of millions is what mostly takes. And now with 1,200 examples, it's already starting to push objects, grasp objects, and so on. I also forgot to put my charger, and it's showing already running out of battery. So this was interesting, but someone can argue it's still very, very hard to find complicated actions, right, like opening bottles and so on. It's still very, very hard to discover. And so in recent work with Rohan, what we have been looking at into is like things like bimanual manipulation, and how can we discover interesting motions? And what we are trying to discover are synergistic motions, right? How should the two arms interact with each other so that you can get this kind of motions, essentially? And our core idea is very, very simple. We are going to reward actions where when two agents perform together, they create a different outcome than when the two agents were not performing in a collaborative manner. So if the two agents try to do it alone, they get some other output. If the two agents try to do it together, they get some other output. So for example, let's consider this lifting bar. The action is both the agents are trying to lift it from their end. Now if the A does, first A lifts and then B lifts, this is what the output will look like at the end of the action. On the other hand, if the both of them lift together, this is what it's going to look like. So we are going to reward actions where when both are acting together, it's much better. It's much different than when both are acting one after another. And so this will help us to discover synergistic motions. And so these are some of the synergistic motion that you can discover. So for example, both agents lifting on a bar, or in this case, lifting of ball. So one agent has to hold so that the ball will not roll, and the other agent tries to lift. And opening of bottle, one agent holds a bottle, another tries to rotate the cork. You can even transfer them from a simulation to real world by some modularity in learning. And so here is an example of transferring to real world. Again, this is all work of Rohan, who's Leslie's student, and he was a great intern. Published 2 papers in one internship. So yeah, overall, I mean, you can see that you can start to do extract some very interesting actions and just by exploration, essentially. Okay, we have been also exploration and navigation. I'm going to jump this part. The last couple minutes only, or 2 minutes only, I'm going to use extra. Another thing that I'm super excited about is this whole idea of democratization of robotics. So the way computer vision and machine learning have changed is not just because there are machine neural networks. It's also because anyone can come into the field and publish papers. It's so easy. The entry barrier is so low in case of computer vision and robotics, like with PyTorch and TensorFlow and so on. This is something which is not true for robotics. It's so hard for someone to build on top of someone else's work in case of robotics. And so I think to have true success in robotics, we really need to cut down this entry barrier and have hundreds and thousands of people come into robotics and do some interesting experiments with robots. And that's when we are going to see faster progress, essentially. So we have been building something called PyRobot, which is an open source robotics platform. It supports things like manipulation, navigation, collecting demonstration, and so on. The idea is simple, right? I mean, we are basically going to abstract all the low-level part. We are going to expose high-level APIs to the person. And so it's basically almost as simple as simulator, like whatever for them doing robotics, essentially. And once it's so simple, anyone can basically bootstrap and basically start building their own robotics lab in a day. It also works on this low-cost robot, which is just $5,000, essentially. Our hope is that once you have common API across different robots, so the multiple robots work with the same API essentially from here on. You can have build data sets. So this place can build data sets which is going to work across different robots. Algorithms will just work by just changing the robot name, and hopefully now you can try to make them work essentially. Once we are talking about common APIs, someone else can develop their own algorithm, upload the code, and now I can test it on my own lab essentially without worrying about whether my implementation was correct or not. This is something which works in computer vision and machine learning really easily, just thanks to PyTorch and TensorFlow and all these frameworks that have been developed. And I think we need something like this in robotics just so that we can build faster on each one else's research. So the goal here is reducing entry into barriers and allowing benchmarking. There are multiple robots already into this and multiple simulators that work with the same API already. And there are like 30 universities already using it, thanks to some push by us. I mean, we basically gave a lot of free robots as well. And so hopefully I'm going to ask you to also consider using it just so that other people can build on your research. It's going to get you much more citations. If you think you're getting enough yet, it's not going to be much, much more. That's the reason why you should do it. All right, with that, I can take at least 2 or 3 more questions. Yeah.
Thank you. Very interesting talk. Interesting work. A question I will have in particular for domains like manipulation and interactions where the robot has to interact with the world and use physics and contact disadvantages. What do you think should we use as an action space? Is images sufficient just as a way to think of how we're gonna act, or are there a layer of abstractions that could also be valuable for this context?
So in a lot of our initial work, we mostly used action space in the form image itself. But the last work, when we are trying to explore this, like Rohan's work, we are starting to use primitives rather than image space, like twisting primitive, reaching primitive, and so on and so forth. So I would say till now we have been very convenient based on application. We just changed the like something based on whatever we are trying to achieve. We basically change the action space and so on. So the right answer, of course, is hierarchical representations, right? So you have to build, for some task, you have to build representations at the bottom level, which is like image level, and then you start learning primitives by a lot of imitation and data and so on, and then you start using primitives and so on and so forth. So the right answer is hierarchical representation of actions, which will allow you to decide on the fly itself like which level of action space you want to be dealing it. In our algorithm, we have been using everything all over. In our talk, I've been using everything essentially. Thank you.
Thank you for the nice talk. And as we noticed that self-supervised learning algorithms always focus on one robot doing one task. And my question is that self-supervised learning algorithm, where self-supervised learning algorithm can bring us to a general controlling algorithm or a specified controlling system focusing on one robot.
Right. So hopefully, I mean, in the middle of the talk, I was talking about already expanding self-supervised learning to multiple tasks, for example. I mean, but you can still argue most of these tasks are still primitive tasks and so on and so forth. But I mean, the idea is the common network backbone can basically maybe start to learn a representation that is going to work across multiple such tasks. And so that's what I was trying to show when I was trying to do grasping, poking, and pushing together. So I mean, in no way is self-supervised learning restricted to do only one task and one robot as well. Similarly, you can get it from multiple robots. You can try to encode. So the common policy learning that I was trying to do, that VH function is something that you can actually learn via backprop, for example, like what your hardware is, the way your hardware is behaving and so on. And so you can again try to generalize across different hardware itself. Now that's something we have not done, to be frank, like learning across multiple hardwares. That is something we should explore. But across multiple tasks we have tried. It seems to be, as I said, working reasonably okay, but we have also not crossed the boundary of more skillful manipulation when it comes to that. I mean, still at least.
Okay, I'll go next.
Obviously.
Okay, here's a hugely unfair way to summarize your talk. Okay, there's this very complicated problem which we call robotics, and the way to move forward is we have to use low-cost robots and make sure that these robots are learning not just on one task but on many tasks and on a large variety of environments, and also that generalize across different hardware implementations. So it seems to me that we're making the difficult problem much more difficult. And I can see how there would be some benefits, but I wanted to see if you also have some ideas about like possible limitations of that, that
Right.
vision.
So actually, I'm going to argue that it's a hard problem, but the richness of the problem is going to bring the solution to it, essentially. So a lot of people also argue that, so this is something which is an argument also in a lot of people throw at me when I argue against simulation, right? It's already very hard in simulation. That's what simulation people will tell you. Like you told me something, I'm telling you what simulation people will tell you. It's already very hard problem in simulation, and now you're trying to make me do it in real world. Why are you doing it in real world? Let's first solve in simulation. That's my characterization of, or that's simulation people characterization of your work. Now, you can argue on that back to them and say, simulation is just such a poor representation of the world. That poorness is making your problem actually hard. Once you have haptics, it becomes easier. Once you have lighting conditions which are varying, it becomes easier. Once you have diversity of objects, it makes you learn actually what the task is. And that is exactly what I'm arguing. If you actually learn the problem in the right way, maybe the richness of the problem will provide you the solution rather than looking in a very restricted way. Now, is it true or not? I don't know. But at least that's a hypothesis I am working with, and I want to see if that's true or not, essentially.
That's great.
Right.
Thank you.
Yeah. Okay.
Sorry.
So there are lots of very hard tasks. For example, let's say you would like to peel a potato that are completely outside of the realm of what's currently possible with current systems. What do you think are the breakthroughs that are necessary to do tasks like that, to perform tasks like that?
So I mean, I actually think that there are two breakthroughs in hardware that we need before actually you can go to even more variety of tasks like potato peeling and even more complicated. The first is the development of good haptic sensors. Now, I know there are a lot of possibilities in the market, but there's nothing that I can just go and buy and say this is going to work for years and years or hours and hours and whatever, like some durable nature, and it's repeatable and it's whatever and so on. So haptics, I think, is very, very critical. The second one, which I have to say I learned very recently, is deformable soft hands is, I think, something I feel very, very critical. Like right now, this parallel jaw is just pretty bad. I mean, all of us will agree. There's no answer to this like very nice skillful manipulation with like Allegro and all that stuff. But now these are hard hands. They are not durable enough. And so that's a second area where I feel in hardware. So I think those are the two things that I will say are critical on the hardware side. And then, of course, cheapness of hardware so that we can have thousands of these inside the real places. And that's already, I talked about that part, essentially. Beyond that part of the talk, like whatever I talked in talk, those are the two things I will say, feel on the hardware side, which will be critical before breakthroughs on those kind of harder tasks would come.
Okay, one more question.
G'day, yeah, really interesting talk actually. I wanted to narrow in one section where you were speaking about how taking the data from multiple different tasks or multiple different locations and how a combination of those data sets proved to be more successful than from a single one with a task that you're actually looking to complete. And you put forward a few ideas and theories of why that's the situation or why that's the case. I was wondering, is there any way we can really get into that sort of phenomenon and dive in and figure out what is it from these different environments and from these different tasks that is useful in the others?
Right. So I think that's a very critical problem and something that I would love to study more myself. I mean, I have to say, this is one of the problems of being doing too many things, and I would say that's my mistake. Like you basically get something interesting, you should focus more on that and to figure out more. I mean, at this point of time, if someone has to make me a guess, I think the answer is in the combination of what he said and what I like. The underlying dynamics is very, very similar of the two tasks, and the amount of data is too small. So what happens is some kind of regularization, and now you get a much better model that you have learned, if I have to make a guess. But then again, you're right. We should study it more because that, I think, is a very, very critical problem of multitask learning. I think in my whole hypothesis, that is something which we need to, the whole thing stands on this one leg is this multitask learning, that I would not need to collect tens of thousands of examples for every possible task. Otherwise, the whole thing falls down to billions of examples, and now we are again stuck in this billion example world. Yeah.